Okay, we are going to continue into chapter 17. Just a reminder that 17 is the last chapter for this first test of this semester. And that test is coming up here in the next couple weeks. So it's on LMS, and it's going to cover basically everything that we've talked about since the break, chapters 13, 14, 16, and 17. So last time, we were in section 1 of chapter 17. And as a quick review, basically, we did equilibrium rate constants. So set it up like this. The coefficients that you balance it out to be as the exponents. Also remember, if anything is a pure liquid or solid, we take it out. And then, of course, pretty straightforward to do the math with it. Now, that assumes that we are at equilibrium. So the concentrations are not changing. And we're at equilibrium. We can look at this numerical value for K. We can say if it's less than 1, that means we have more of our reactants. If it's greater than 1, we have more of the products. Now, perhaps we are looking to create something, but the equilibrium value for that reaction is less than 1. That means we're not going to get a whole lot of it. Okay. Well, if we want to get more, we have to do something to get more. And so we're going to talk today about how can we shift equilibrium. Okay. And so when we say shift equilibrium, basically what we mean is, okay, we have more of our reactants than our products. How can we make it so that we get more products? How can we force more of this reaction to go that direction? And that's what we mean. We'll say things like shift to the right. Okay? And if we shift the equation to the right, then, well, we get more over here. If we shift it to the left, we're going to get more over here. And so basically, when we talk about shifting equilibrium, there are 3 different options. It can shift it to the right, it can shift it to the left, or it can make no change. That is an option. Okay. So shifting to the right means we're getting more of our products. Shifting to the left, we're getting more of the reactants. So how can we do that? Well, the whole thing with shifting equilibrium, it all comes down to something called Le Chatelier's principle. Now, Le Chatelier was a French chemist. If you look at his name, you can tell that it's very French. It looks like it should be pronounced Le Chatelier in English. but he's French, so it is Le Chatelier. And basically, he said, if we have a system, and we'll consider, the entire reaction and everything that's happening in it. If we have a system that is at equilibrium, we can put a stress on the system. We can stress the system, and it's going to react by trying to come back to equilibrium. So how can we stress this system? Well, we change something. If it's at equilibrium and you change something, there's a good chance that other things are going to change as well. Think about it, if you are balancing something, okay? So if you're balancing something, about balanced, close. If you add weight to one side, well, to come back to equilibrium, you have to add weight to the other side. Okay? And that's sort of what we're talking about. We're going to, like we said, we call it a stress. So you're going to stress the system, and it's going to make some changes, maybe. Some of the things we talk about, there will be cases where you change something and it doesn't do anything. So not every stress makes something change. But anyway, so let's talk about some of the ways that we can stress the system. Now, the easiest thing to do is change the concentrations. Remember, if I change this concentration, in order to keep this value the same, I have to change some of these other numbers. Okay? To change something else. So, let's talk about changing concentration. Well, one of the easiest things you can do is just add more reactants. And that makes sense. I mean, honestly, you shouldn't even really need to apply Le Chatelier's principle to that. If you start with more of this, you're going to get more of that. It just makes sense. Okay? But when we think about it as, Le Chatelier, okay, adding a reactant puts a stress on the system. Okay? It increases these concentrations right there. And so in order to balance out, to get the same value for K, we have to add some of these. Now, if you want to really, truly talk about everything that's going on, when you add more of the concentration, by the time you get back to equilibrium, these two values will have gone down because they get used up. But anyway, if we add reactants, equilibrium shifts away from the reactants. And what happens is, good thing you made it on time. So if we add more of this, we get more of that. So, the thing is, it works the other way too. If you add more products, it's going to shift back to the reactants. Now, why you would want to shift it back to the reactants? Well, in most cases, you're not going to. Because, this is what you started with. Why are you doing it if you want to get more of that back? I honestly can't think of an example of why you would want to right now. But if you did, you could do it. Okay? And so that should show a bit of a pattern. If you ever add something to the reaction, equilibrium is going to shift away from it. Okay? So if you add it over here, equilibrium shifts to the right. If you add it over here, equilibrium is going to shift to the left. So wherever you add something, equilibrium shifts away from it. Now, in a very similar technique, what if instead of adding something, we take it away? Okay. It's possible that as this reaction is going, we can actually take these things out. Different reactions, you do it different ways, depending on what these products are. But once again, that shifts things. So if we take these values here and lower them, it has to shift to keep that value where it is, keep that same numerical value. And so if you add something that shifts away, it would make sense that if you take something away, it shifts toward that. So if we are removing these products as they're being made, it forces all of this to keep going to try and get to equilibrium. Okay, it wants to get to the concentrations that are going to give us this value. Okay? And if we keep taking these away, then it keeps trying to make them. And that actually we do quite a bit in industry. If we don't have a really great K value, we start the reaction and then we start taking out what we're getting, because then that forces things to keep moving. So changing concentrations, we can add or remove, and we can do it on either side. Once again, anytime you're trying to get more of your reactants, it's not going to be very common, but you might want to do it for some reason. But if you add something, equilibrium shifts away from it. Okay. If you add something, equilibrium shifts away. Right. So if we add it over here, it shifts this way. If we add it over here, it shifts that way. If you take things away, equilibrium shifts towards what you're taking away. So if we take away these, equilibrium shifts this way. If we take away these, it shifts that way. Okay. So concentration. We can change concentration. All right. The next thing we can do, or the next thing that the book talks about that we can do, changes in volume and pressure. Okay. So obviously, if we're dealing with volume and pressure, we have to have gases. Okay. So this reaction that the book gives as an example, okay, we take carbon monoxide, and we're reacting this carbon monoxide with hydrogen gas. It is a reversible reaction, and it's going to produce methane and water. Okay. Now, we kind of have to think back to our gas laws. Okay, and Avogadro's principle. And remember that the number of particles is related to the pressure and the volume. Okay. The pressure and volume related to the number of moles or number of particles. You can think of it either way. It's pretty much the same thing, just a different unit. Anyway, so if we change the pressure or the volume, and changing the volume changes the pressure. Remember, we talked about that. If you decrease the volume, it increases the pressure. So anytime you see a problem that talks about decreasing the volume, think increasing pressure. Okay. When we are dealing with this, what we need to do is we need to add up the total number of moles of gas on our reactant side and our product side, based off of the balanced equation. So here we have 1 implied. So we have 1 mole plus 3 moles. So over here, there's a total of 4 moles of gas. Over on this side, we have 1 and 1. So we have a total of 2. And now that we've done that, we can say, adding the pressure, adding more pressure, or decreasing volume, it's the same thing. In order to relieve that pressure, in order to relieve that stress, we are going to we're going to shift towards the side with fewer moles. Because if we create, if we use up these to create this, our N, the total number of moles that we have, is going to go down, which will relieve the pressure. Because if you have fewer moles, you have lower pressure. Okay. So, in this case, if we were to increase the pressure, we would get more of our methane and water vapor. Okay. If we have the same number of moles on both sides, changing the pressure is not going to do anything, because there's no reason to. It's not going to change the N. So if, just hypothetically, if this balanced with a 1 right here instead of a 3, we'd have 2 and 2, pressure wouldn't make any difference. But in this case, because we have that 3 to balance, we have 4 and 2, so increasing pressure shifts towards the lower number of moles. So. Okay. And then we can mess with temperature. So remember, some reactions are exothermic and some reactions are endothermic. We did skip over chapter 15, but remember I said, if we ever need those concepts, we'll just explain them real quick. This is one of those times. The book is going to give you a value called delta H. Okay. It actually has delta H naught, but anyway, so delta H. Now this is a measure of energy. Okay. It's measured in joules or kilojoules. If you have a negative value, so if it's negative, it's exothermic. Exothermic. We're generating heat, okay? And this is the easiest way to think of it. And I shouldn't have erased that equation because we're using it again. Now, if it's exothermic, what that means is we can consider heat to be a product. We're making heat. It's one of the things that we're making is heat. Okay? And that makes it a lot easier to think of with the with how equilibrium is going to shift, because you can treat it just like anything else. So let's say we take this whole thing and we put it inside a freezer. Well, what's that going to do? It's going to reduce the amount of heat. The heat is going to move out of that system into the freezer. And because of that, well, if we remove a product, it shifts that way. If we remove a product, it will shift towards the product. That's the easiest way to think of it, is that just say, okay, heat is either a product because it's exothermic, or if it's endothermic, so delta H naught is going to be positive, endothermic. And honestly, we can just write this the other way. So we would say heat plus methane plus water vapor create carbon monoxide and hydrogen gas. So if you had methane and water and you wanted to convert it into carbon monoxide and hydrogen, you do. That would have a negative, or would have a positive delta H naught. So we would think of heat as a product, or a reactant, sorry, a reactant. And in this case, if we wanted to get more, well, we'd add more heat. We would heat up the methane and the water, because that would mean we were treating it like a reactant instead of a product. So heat, the easiest thing to do is just treat it like either a reactant or a product. If it's exothermic, it's a product. If it's endothermic, it's a reactant. If you're given delta H's, negative means exothermic, positive means endothermic. And you can see how there's actually a visual representation on page 610. and it's talking about a couple of different gases. And so we've got dinitrogen tetroxide. And this can spontaneously decompose to form nitrogen dioxide. Now, the dinitrogen tetroxide is colorless. Nitrogen dioxide is sort of a reddish brown. Now, the delta H naught for this is 57.2 kilojoules. All right. Now, that's the delta H naught as it's written. Remember, if it's written the other way, things change. Okay, we just want to make sure we remember that. We can shift this equilibrium. Okay, so it's a positive one. So it is the endothermic. I don't know why it took me so long to come up with that. So we can put it over here. Okay. So if we add heat, if we add more heat, it's going to drive it that direction. You can see that in the picture. Okay. We've got that container that's holding this gas, and we put it in warm water. Okay, that drives it over here. And you can see that the container is a nice dark reddish brown. But when we put it on ice, it's like taking this away, so we get more coming this direction. Now, it's not completely colorless. We still do have some of this in there, but you can see that it's actually a much lighter color, indicating that we have a lot more of this colorless gas. So the things that can change equilibrium: concentration, pressure, or volume, same thing, and temperature. One thing that does not shift equilibrium is a catalyst. Now, a catalyst can make you get to equilibrium faster, but it doesn't change where the equilibrium is. Okay? So there are three things that we need to be concerned about with shifting equilibrium, Le Chatelier's principle. These three stresses: okay? Changing concentrations, changing volume and pressure, and changing temperature, if we're dealing with something that is clearly exo or endothermic. If your delta H naught is very, very small, yeah, you'll shift equilibrium a little bit, but it's typically not going to do that much. So, okay. All right, that's the end of section 2. So we're going to stop. We got a half-hour worth of new material today. So we'll stop and let you get started on some homework. Most of the homework is going to be look at a situation, and it'll say, okay, either how can you shift equilibrium, or if you do this, how is equilibrium going to shift?